As you that are familiar with tunable diode laser absorption spectroscopy sensors, they're pretty expensive. And so I'm exploring ways to bring down the cost of these sensors to make them just as quantitative, but exploring ways to bring down the cost. And I think one way to do that is to use optical bandpass filters that can be tuned in real time. And I came across this potential opportunity. It looks like it's a technology that came out of AFRL, and they've got a patent here. So what I've done is just try to simplify the basic concepts, and then probably in later videos as I try and figure this out to see if it's worthwhile to implement on a sensor, on a TDLAS sensor. We'll dig in further into some of the details around mode selection and actual design of the filter. But it allows for super fast tuning. It's kind of limited only by the charge up and charge down of this capacitor. So let's get into it. Okay, the best way I've tried to make sense of this is that there's, let's see here, shared substrate, crooked lines. Okay, and then we have, it's essentially two systems here. There's a WSF, so wavelength selection filter. And then, I could be wrong here, but this is the patent files sometimes are a little dense and hard to figure out, but this is just kind of a top level. I think this is how this is working, and I'm going to keep digging to figure out exactly how this works. So this is order selection filter. And so presumably you have, at least the way I'm thinking about using these is you have maybe some broadband light source out here. Where intensity, you're targeting this region, which is somewhere in the near to mid infrared. Just call it, I don't know, 2 micron. That's kind of how I envision this working for absorption spectroscopy sensors. So let's try and explore this a little further. Okay. So let's take a look first at the wavelength selection filter. And so the way it's described is, I take it there's lithium fluoride. There's essentially these sections of there's these thin sections of lithium fluoride and gallium arsenide. And then you have this thin film capacitor, which is GZO and some sort of aluminum oxide. And that's sandwiched in between another set. The extent of how these are, the number of these pairs, I'm not sure on each side, but essentially there's presumably some number of pairs, and it's these are all stacked, and there's some sort of power supply. 30 volts or something. That I think I'm gonna get into on the specifics later. But essentially, this thin film capacitor, it's charged, downcharged, and so as the impedance changes with the charge, so does the index of refraction change. So if you remember from the optics course, relative permittivity and permeability, I think I have those right. So this is permittivity is changing with impedance changes in this thin film capacitor. So that changes this guy, and in return, that's going to change the index of refraction. And the impedance matching through this stack here, shifts the wavelengths. So I suppose there's some sort of impedance matching between this thin film and these other sections here. And so then that dictates, filters, and selects the wavelengths that get transmitted through. And so I think the key here, what these researchers have identified and kind of what makes this work is that the high order capacitor has something on the order of m equals 14. And there's some sort of overlap with the band gap of the material that's being used. In this case, these guys here is GZO and aluminum oxides. And so the combination of the order of the material and the band gap. I'm no material scientist, but we'll dig into that later. I think the key here is that it allows you to shift transmission of the light that's coming out here into the shortwave infrared. And so we're looking at 1.4 to 2.4 micron. So that's pretty key. I mean, that's pretty ideal spectroscopy range there. So there are two components to this. There's the wavelength selection, and then there's the order selection. On the order selection side, it seems like we've got some sort of mirror. It's got titanium oxide leads, electrodes that can be used to also apply voltage to the material. And then so this allows you to select, say we're looking at what's being transmitted out here from the input, or from the output of this wavelength selection criteria. Let's say we've got something like, wavelength 1, 2, 3 micron. And let's say the transmission peaks for these guys are, I think what they specifically cite in the patent is in the range of 1.2 to about 2.25. And so what this piece here allows you to change also the index of refraction. So then again, there's some matching that happens between the wavelength selection and the order selection. So it allows you to just essentially tune to one of these, any one of these transmitted orders of light that gets through this stack of thin films. And what's key here too is that this bandwidth is pretty narrow. It's on the order of something like I think it's 0.4 nanometers. So then you start to get in the range, for those of you familiar with tunable diodes, distributed feedback diodes, for example, that I'm used to working with. It's probably on the order of this sub nanometer bandwidth, and so you start to get into the range where you can fully resolve some of these absorbance spectra for methane, CO2, some of these atmospheric molecules or combustion-related molecules. And so then the tunability across this, so you can modulate the wavelength over which this is tuning, and that has to do with the capacitor charge and discharge. And so according to the patent, that's something on the order of 22 microseconds. And that translates into something like 45 kilohertz. So well within the striking distance of TD-LAS applications. Again, just to kind of illustrate my thoughts on how this would be applied, is you have some sort of broadband light source somewhere, around 2 micron transmitted intensity. And then that gets emitted. You have some sort of electrically controlled or tunable filter. And so on the other side, you get this really narrow bandpass filter, very narrow output. And so then that can get tuned in wavelength space. And so, you start to be able to resolve absorption features. So that's kind of the big picture idea of this patent. I think the key is, you have these two different kind of subcomponents within this filter, and there's the wavelength selection. So there's some design criteria that probably goes into this big, large stack on selecting the right wavelength. And then you have the order selection, which lets you choose of those few select regions that get transmitted, which order do you choose? And so then allows you to focus in on the really narrow band passive light that's being transmitted for your tunability. Pretty neat. Need to dig in a little bit more on the dielectric side of things. Not exactly sure. I think there's some constructive interference that's happening that's allowing the transmission to occur, but just need to dig into that stuff. So this is kind of what I'm thinking. Love to get your thoughts, any questions. If I messed anything up, let me know. Thanks.